So first of all, I just want to acknowledge everyone that's worked on this this work. They're all listed here. I'm not going to go through them individually. It's just showing that there's been a lot of involvement from a lot of different people at a whole different range of levels, from workflow development, interpretation, data acquisition and processing. So I just wanted to start off by giving you a very, very high level overview of what we're going to be looking at. So all the airborne electromagnetic conductivity sections, so the model data, will be in this color ramp. So basically that's, let's see if I can get my mouse to go there. No. Oh, I can't see it. Anyway, so resistive rocks will be in blue, and you can see there is the so the igneous and metamorphic rocks, sandstones to moderately conductive, to mudstones, which are generally more highly conductive, to massive sulfides, which are right down the warmer colors. However, that is very dependent on actually what type of the level of weathering, and also the presence of water in the rocks. So saline water will make a more conductive rock or conductivity signature, and fresh water will also look more resistive. So just to give you an idea of what that looks like in a sort of more real world example, if we look at that figure on the bottom there, we can see that there's a more conductive unit that's overlaid by a more resistive unit, and then again overlaid by another more conductive unit. And so if we do a rough interpretation of that and then look at some of the geology, we find that those more conductive units are more mud rich, they're mudstones, and the resistive units are sandstones in that example. So that just gives you an idea of what we're going to be looking at in terms of color scales. So I'm sure a lot of you are probably well aware that a large part of Australia, or a large part of the cover is well, the older rocks are covered by younger sedimentary Cenozoic basins and regolith as well. So in this area, as you can see there, the those sort of beigey, yellowy colors, they look almost white on the screen we're looking at here, are the Cenozoic cover. The green there is the Carpentaria Aeromagnet Basin, and the blue here is the Georgina Basin, and they're overlying the those Mount Isa rocks, which are in that the browns and the pinks and purples. So we can see there's a vast amounts of cover over this prospective area. And a lot of our understanding on the rocks in this area is based on these kind of data sets and scattered boreholes and geophysics, so gravity magnetics typically. However, we've got a new well, it's a geophysical data set, but it's regional, so it covers large areas. It's non-invasive, it's cost-effective, and it's homogeneous. So we can actually use this. We can do an interpretation of that. So what we're seeing here is some structures, some different aged rocks being interpreted, and now we've got a very busy slide. But what it's just trying to illustrate is that we are moving to a more 3D style of mapping through that cover and getting an idea about what we can see, and some of the depths to those prospective rocks and the thickness of that cover. So when we're working at such a like a large scale, looking at the continental scale geology, we found that the best chronostratigraphic scale to work at is the geological error scale. So what that means is that will be the breakdown of the Proterozoic rocks overlain by those Paleozoic basins, Mesozoic basins, and that widespread Cenozoic cover that we talked about. And it's the delineation of these chronostratigraphic boundaries is what we set out to do for our interpretations. And as you can see in that cartoon on the bottom, that helps us highlight where those the basin boundaries and the contacts are, to give us an idea of those cover thicknesses and depths. And so why is that important? Well, those overlying units are prospective for groundwater, and they have minerals and energy resources, but they obscure our access to more, I guess, prospective rocks at depth. So that are more prospective for energy, groundwater, and minerals. So just another way of describing our aims here is we will look at the depth or that thickness of cover. We will reevaluate basin boundaries. So underneath, especially in like those covered areas where we can maybe interpret the distribution of undercover basins. Look at paleo valleys because they are highly prospective for groundwater resources, and also discrete electrical conductors because they could have implications for mineralization. So to do this, we've had to develop a new workflow. And the reason for developing this new workflow is because of the requirement to capture and attribute a large amount of interpretation-specific metadata to our interpretation lines. Some examples of the metadata that we capture is on the left-hand side of or the right-hand side of the slide here. So stratigraphic units, their stratigraphic unit numbers, the confidences of these. So those units above and below the lines that we're interpreting, the confidences of the line placement, contact types, basis of interpretation, new observations, a whole range of things. And the stratigraphic unit information that we capture is consistent with the Australian Stratigraphic Units database, where all our units are current geological units in the database. So a very high-level overview of how this workflow actually works. So we take an image of the conductivity sections and we bring them into a GIS package. This is where we do our interpretation of the line work and also capture those attributes as well. So attribute those, those attributes to the lines. Then at this stage, we run our interpretations through some code that's been written here in-house. And we validate our interpretation. So for example, we would check it against the Australian Stratigraphic Units database. If there's any errors there, so mismatches between unit numbers or stratigraphic units, names, or typos, or anything like that, that we flagged, and then we can go back up to the interpretation and fix them at the interpretation level. And you can see in the top red box, there's a bit of a decision tree. So once we are sure that there's no more interpretations, we pass any errors, we pass that validation, then we can continue down our workflow and we can take our two-dimensional interpretation lines and interpolate and extrapolate their coordinates and project them into a 3D space. And then we can bring them into a range of 3D packages. And we can also extract the depth estimates with all the attributes for the estimates of geological and geophysical surfaces database, also known as AEST. So this workflow has been made as sort of open format as we can possibly do. So it works on various GIS packages, and it exports data that's not bound by any proprietary limitations that can go into a range of 3D software packages. And we're currently working on making this workflow a lot more accessible. We're rewriting it in, so it's going to be in multiple programming languages and packaged in a nice little standalone executable that can be, a lot easier to package and share with people. So it's going to make it a lot easier for people to actually use. We've also written a step-by-step instructions, so like a standard operating procedure, which has a whole bunch of information about how to set up workspaces, you know, the interpretation guide, how to use confidence levels, so trying to take the subjective nature away from that, and explanations of the fields, and really just it's got a step-by-step of how to do the whole thing. But we've also recently published a workflow document that, yeah, this is just a much more high level. It's not to that detail, but it just tells how we do the interpretation, and how the workflow actually works. So sort of more onto the interpretation side of things now. When we do our interpretations, we don't do them in isolation. So we take into account a huge amount of other data. So for example, the information that's delivered in the multiplots. So some of the some examples of what we can see there are power lines. So the power line monitor, you can see these spikes correlate with these discrete electrical conductors. If we're just looking at the lines, we could see things that look, you know, potentially like something very interesting. But if we have to look at, take into account that there's a lot of things that can interfere with the acquisition of the data. So the power line monitor is very important. Likewise, the spherics, so atmospherics, this is lightning. You can see is going a bit off the chart there, and we're getting a similar anomaly or artifact, sorry, where we're seeing these discrete electrical conductors as well, and some noise. So we have to be cautious of these things. Also, the instrument geometry. So so for say a fixed wing with a bird, there's roll, pitch, and yaw, and the bird and the plane can also get out of sync, I guess. And when we see things going off the chart, then we can get, as you can see on the bottom, some discrete electrical conductors, which, you know, we have to take with a grain of salt. We've got that little topographic rise. Maybe the plane had to, you know, change its elevation, and we're getting a bit of instrument geometry movement there. Data misfit, so how well the models fit the data is also very important. And as you can see here again, it's going off the chart, and we're getting some noise at the bottom there. So it's just another thing to look out for. And the depth of investigation, which helps us get an idea of like what depth that signal penetration was, and be cautious of interpreting anything under these big conductive bodies. So we also integrate the AEM with a range of different data sets to help us get our best out of the interpretation. So the other potential fields, such as the gravity and magnetics, digital elevation model, very useful is draping the surface geology on the digital elevation model. That helps us see how some of these basins can come up to the outcrops, stratigraphic boreholes and petroleum wells, water bores, mineral occurrences, mines, infrastructure, and so on. We also integrate our conductivity sections with seismic to see how we can sort of extend stuff to deeper areas and vice versa. A lot of these data sets that I'm showing at the moment are available on our GA portal. Here's just another example of how we integrate our data with other data sets. So here's the conductivity sections integrated with, this is seismic interpretation in the Canning Basin. Those purple lines there are the base of the Grant Group, and we can see that there's some areas here where we've got sort of on the left, middle of the left of the screen, we've got quite horizontal flat-lying beds, and towards the center of the screen they get a bit deformed and disrupted, and they go to deeper areas, and we can sort of see that a good correlation between the seismic interpretations and what's in the airborne electromagnetics as well. So here's just some examples of some of our observations and how the AEM can be really helpful, sort of addition to the geophysical data sets and geological data sets that we already have. So here we're in the Camel Wheel area. This is a very old map from the 60s, and right in the center there is Lady Annie mine. Just to make it a bit more current, I've added the major mines and mineral occurrences. And you can see that these things are potentially structurally controlled because they fall sort of near these faults and sort of bound by some of the faults. If we look at the magnetics, we can see that they're associated with these magnetic anomalies. They sort of fall on the edges of these anomalies. And if we look at the gravity, and it's not the best, but if you squint really hard, you could potentially see that they're falling on these ridges as well. And these are the geophysical data sets that are typically used in that first stage of exploration. But they don't really give a very good sort of depth feel to them. Like you can, get an idea of the depths of features, but they don't really give you that sort of that 3D cross-section type information. And that's where the AEM comes in. So at least in that top 500 meters, we can get a much better feel for the geometry of these things. So this is sort of showing that that conductor on the left there is showing that, well, it falls within the bounds of those faults. So it's likely these things are structurally controlled. And then we can actually get a lot better understanding about the geometry of the mineralization or the host rocks as well. But what's really powerful with the AusAEM is that it was flown regionally, not only in these highly explored areas, but also those underexplored areas. So if you look up strike of some of these faults here, there's an area there where there's no mineral occurrences, no major mines. And then if we jump across 20 kilometers to the next line, we get similar features in the AEM. And this is like really important because a mineral explorer has gone out there and they've used the AusAEM and they've seen these conductors and they've reanalyzed boreholes out there, and they've had a technical success where they've found some copper mineralization, and they're planning a new borehole drilling program as well based on some of these findings. So it's a really good example of how the AusAEM can be used for exploration. So just jumping out scales here now, this is quite a large area that's about 150, it's about 300 kilometers by 150 kilometers. So it's quite a large area. You can see that there's this conductive feature running sort of through the center there, which correlates very well with a magnetic feature as well, and it's sort of truncated, and we sort of lose it on the left-hand side where we've got more resistive rocks, and we don't really see that magnetic feature either. If we bring in the gravity, we see a similar correlation between the gravity, magnetics, and the AEM, that there's some kind of large-scale feature there. So if we look at this area in the box in greater detail, so the AEM was diverted for a borehole in that area. That borehole intersected this conductive feature too. If we look at the, I guess the magnetics in more detail, we can see that the magnetics and the AEM correlate very well with what we're seeing in the AEM, and what we're seeing is, as a conductive feature, is that magnetic feature that I've highlighted there. So if we bring in the surface geology, we can see that outcropping in this area is a pyritic black carbonaceous shale, and that's the same unit that was intersected in the borehole. And this makes a lot of sense, because if it's a carbonaceous shale, then it's going to be a conductive unit. If it's pyritic, there's sulfides floating around in there, it makes it, even more conductive. And then, if there's sulfides floating around there, maybe there's some magnetite, pyrrhotite floating around too. That could explain that magnetic signature that we're seeing as well. So this integration of data is really aids the interpretation of the AEM. but it really helps us get an understanding of how some of these units can be extended to deeper areas as well. So this unit only outcrops in that area that we're looking at here in the more detailed box, but we can use the AEM and this integrated approach to extend the distribution of a unit such as this to great distances from where it's actually outcropping to over 50 kilometers to the north and about 150 kilometers to the southeast. And in some places, you can see that just 2 lines down from the box, we've got over 200 meters of resistive cover overlying that unit. But because it's resistive, we can see through and we can continue to map it in the AEM. And this is really important because about 150 kilometers to the southeast, we have units of the same group outcropping, which really helps us to actually constrain and confirm that distribution of those rocks undercover, that they do extend to that area. And yeah, so that could have great implications for exploration, because if units such as this were found to have economic significance, then the AEM can be used to constrain targets, broaden search areas, and also reduce exploration risk and costs. So even a larger area now, so we're looking at 300 kilometers by 400 kilometers, and I'll just let you know that that main figure has north to the right-hand side of the screen. So that's in this area here in the central Northern Territory. And what we can see there is there's these rare scattered Proterozoic outcrops in those darker brown colors, and then everywhere else is pretty much cover. We do have an inkling that in the north there might be some kind of Paleozoic units. So there's somewhere in there that there's a transition from a Proterozoic rock to a Paleozoic rock, but as far as we know from the surface geology, that's all we can see. But then when we bring in the AEM, we can start to see a huge amount of detail straight through that cover. First of all, we can see a major structural feature through that area, separating the Proterozoic aileron province to the south, which is on the left of the screen, that more resistive rock, from this more conductive rock in the north, which is the Lander Trough of the Waiso Basin. And so upon further investigation, the distribution of this unit was integrated with the major crustal boundaries from Corche and Dublier, and it had almost a one-to-one match of that same boundary, and that's known as the Wallora suture. So the Wallora suture was interpreted from seismic data and some magnetics and other geophysical data, but it was never interpreted to come so close to the surface. So what we're actually seeing here is the near-surface expression of that major crust boundary, the Wallora suture, under just thin 5 to 10 meters of that Cenozoic cover. Now, this has like great exploration implications, because these major crustal boundaries, they're known to be, or they could be, fluid flow pathways for mineralizing fluids to upper crustal levels. So they can, to see this so close to the surface is actually quite a good discovery with the AusAEM. I also integrated this with a digital elevation model. As we can see here, the cooler colors are low and the warmer colors are high. And there's quite a significant offset along this fault as well, which suggests that there's been geological movement, a geologically recent movement along this structure, which also has implications for hazard mapping and neotectonics. So it's just another way we can use the AusAEM in this way, having this regional AEM data set. And there's just an example of just how we can also map some of those things that I said on one of the first slides of basin boundaries and undercover stratigraphy. So if I just put the surface geology back on, you can see how we're moving to interpreting the geology in a more 3D sense and really starting to look undercover. So about a decade ago, GA delivered the WASANT, Western Australia, South Australia, Northern Territory Paleo Valley dataset. As you can see here, those sort of orange basin outlines are the interpreted paleo valleys. And they did an excellent job of mapping where these paleo valleys lie, but they didn't have a regional AEM dataset to actually interpret the undercover distribution of these things. So now that we have this dataset, we can go in and look at these paleo valley datasets and really refine them. So if we look at the ones in this area here, and we peel off the cover again, you can straight away see that there's this basin-like structure overlying, more conductive basin-like structure overlying that more resistive Proterozoic aileron province. If we do our interpretation of that using that integrated workflow, and then we have a look at it against the Paleo Valley WASANT dataset, we can see that there's areas where we can quite significantly increase the undercover distribution of these paleo valleys based on the AEM dataset. And we can also see that there's areas where the connectivity between what have previously been mapped as two paleo valleys can actually be connected. Now, these observations are really important because paleo valleys, they're known to be groundwater conduits. So understanding their connectivity and their volume is very important, especially somewhere in Central Australia. So we, if we just bring the surface geology on again, you can see how we've gone from quite a lot of unknowns till we start to really map through that cover and understand the undercover geology, at least in that near surface. Now we're going to talk about something quite different. So hydrogen is very much the flavor of the month. And so some great investigative work from Wayne here in the room was looking around and start to see some interesting things with salt structures, and salt has been identified as an underground storage site for hydrogen. So what I did was I got a data set from WASANT, no, not WASANT, WAPIMS, the Western Australia Petroleum Geothermal Information Management System, and downloaded some shape files for their known salt structures and integrated them with the AEM and other geophysical datasets and geological datasets. As you can see here, so that pink snake-looking thing is a known salt structure. Underneath, we've got the magnetics. It's slightly offset, but you can see that there's some kind of feature in the magnetics that correlates pretty well with that. It's offset because it's below the AEM. In the gravity, there's a similar correlation between this thing and a gravity low. And if we just did a very rough interpretation of what we can see there, there's again those flat-lying horizontal beds in the AEM that are truncated by something or disrupted by something in this area. And then if we bring that shapefile back in, we can see that it correlates extremely well with what we're seeing in the other data sets and the known salt deposits. So this got us thinking. So we went around and integrated these features with a whole bunch of different the AEM with other known salt features. So this is the Frome Rocks salt diapir. You can see in the center there. What we're seeing there is not actually the salt. It's not halite. What we're seeing there is the brecciator zone above the salt, but it's still disrupting those beds. There's here is another the pink sort of worm-looking thing is the shapefile from Western Australia, and you can see again that there's those horizontal beds that are disrupted in places by what could potentially be salt intrusions, and we can potentially refine the distribution of that salt using the AEM. This one, we can see that where the interpreted salt exists could actually be extended for quite a fair distance to the north, and that's based on that topographic high, and also some other features there, which are the conductive, which could be the weathering of the salt. So yeah, it's just an example of how we can potentially extend the distribution of these salt features to greater distances of it undercover. And this one was just a point data set, but but you can see that in the point fell around the center of that. I've got like a dashed polygon there, and again, we've just got that horizontal conductive, what looks like bedding, that has been quite disrupted in that area. So we could actually go from a point to more of a polygon data set, thinking about the undercover distribution of these features. And that was also done with a more integration with the other potential fields to really sort of nut out the distribution of that undercover. So yeah, what this is really useful is informing those studies that are going ahead to look for geological underground storage sites for hydrogen. So the workflow that we've developed has allowed us to interpret large parts of the Australian continent. So we've collected over 600,000 depth estimates. Each of those have been attributed with that geological information, and some of them are already available through AEGS. And that covers a huge area. It's like 2 million square kilometers, or the size of Saudi Arabia or something like that. So it's massive, and that's every 20-kilometer line-spaced in AEM lines that we've interpreted. So just a quick look at what the interpretation looks like. So here's the interpretation in. Oh, it's coming back. So we're stripping through the interpretation. So the Cenozoics being stripped off, and then the Carpentaria-Eromanga Basin in blue being stripped off, and then in green we have the Georgina and Wiso Basin. So we're stripping off each of one of those geological errors till we got some of the oldest interpretation in that area. So this data set in Queensland Northern Territory produced roughly just a bit under, I think, 200,000 depth estimates, each attributed with that geological information. The lineworks are available on our portal through ECAT, which is our electronic catalogue, and there's also a extended abstract written up about this as well if you're interested to know more about that. Here's an example of some collaboration we did with the Geological Survey of New South Wales, where they were interested in using the workflow for the interpretation of the Cobar AEM survey. So we designed a bespoke version of the workflow to allow them to capture their specific attributes that they wanted to capture, and also, and as you can see here, it's a different color symbology as well. And this was a great example of a collaboration where the Geological Survey was able to produce data sets that are fit for our AEGS database. So we helped to provide this workflow and that support, and they were able to develop an interpretation that is fit for our databases, which can also be made publicly available through our database. Oh, and if you're interested, there's a really good report written up about that as well. So yeah, I recommend having a read of that if you're interested in AEM interpretation, because it's got a lot of good information. So the work looking at the salt diapirs led to this collaboration with the University of Queensland. where we interpreted the Canning Basin AEM interpretation, AEM conductivity sections through there, and that was to look for evidence of those salt features, and also collect that multi-layered chronostratigraphic interpretation in the area. And the cool finding here was that where salt had been interpreted to exist, we had those flat-lying, quite undeformed beds, but where salt had been interpreted to be dissolved from other data sets, such as seismic, then we had a lot of disruption in the AEM, and that was that was interpreted to be subsidence and deformation due to the dissolution. So the AEM could actually be used to as a proxy to where maybe salt exists and where it has been dissolved. And this is super hot off the press. I just put this one together this morning, and this is just the Eastern Resources Corridor is where we're working at the moment. And this is in the, it covers prospective areas such as the Kernomonan province and the Delamerian origin. And I'm working to just QC this at the moment, and we aim to get this out publicly in the near future. So, yep, as I said, you can see that we're working towards that national scale coverage of airborne electromagnetics, but also chasing the acquisition is the interpretation, and it's really going from that geological mapping in a 2D sense to really starting to think about the undercover geology, or the upper crustal sort of near surface geometry and stratigraphy. So our interpretations are stored in the AEST database. As I mentioned before, they're estimates of geological and geophysical surfaces. So these are available on our portal, and so too are the cover models that are generated from these depth estimates. So depth estimates from the airborne electromagnetics and other data sets such as boreholes, depth to magnetics, and we're working on getting MT and seismic into EGS as well. Those are a one-stop shop for depth estimates, all formatted at those major chronostratigraphic boundaries, which we can extract and model. So, such as this cover model in the Northern Australia. These cover models have been generated, as I said, for those chronostratigraphic boundaries, and they can be imported or used in other products at Geoscience Australia, such as our mineral potential mapper and our economic fairways tool, which is a minerals extraction economic viability tool. And so just some access channels to our data. We have, you can go to ECAT. You can get the interpretations that are currently available there, and also the extended abstracts to learn a bit more about our interpretation. So there's one on the Canning Basin on the hydrogen storage potential, one on the AEM interpretation in the Northern Territory and Queensland, and you can also get the workflow from ECAT. And the data are available for visualization and download through our portal as well. And also, if you're interested in the very important airborne electromagnetic conductivity sections, which underpin this work, they're also available on the portal as well. So that's about it. Yeah, it's just there's a whole lot of different things that we can do with the AEM interpretation, and we aim to do as much integration so it's as consistent with other data sets that we're producing as possible. For example, our solid geology mapping. So there's a lot of collaboration with internal and external partners, and yeah, it's a huge amount of work, and we're hoping that it's very useful to a wide range of people as well, in academia, environmental managers, resource exploration, hazard mapping, and so on. So thank you very much.
extensive application of AEM data. Any questions? Any questions from the room?
So,
No.
with regards to your basing all your interpretations on GA layered earth inversion,
yeah,
which I think is a one-dimensional inversion.
Yeah,
do you ever,
deterministic, yeah.
For particular areas, try using different modelling or inversion?
It's a very good question. I actually have a slide that can help there. So what we're doing with the people in our gap section are working on getting our probabilistic inversions done at 500 meters along the line. So it's too computationally expensive to do the whole every sounding, and that's producing really good data sets that we'll be able to use in support of what we're doing here with the deterministic inversions. That's very early stages of work at the moment, but what we could do, if I just sorry, I'm just going to, yeah, so here. So what we could do in the interim is we've got a basin here, a conductive basin. It could be very tempting to do an interpretation like this, but the base of that might not actually be geological. That could be the depth of signal penetration, and the actual real basin might be more like this. And so our interpretation would be quite wrong in that area. So what we could do is run a probabilistic one-dimensional inversion just for that one sounding right in the middle of it, and that would run 250,000 models, and then we'll get like an ensemble of models that will give us a lot better understanding about the tightness of this probability map here. It would show how confident we are that those models are good to what depth. So if they're nice and tight, then we know that all the models are really pretty much saying the same thing. And if they span out, then we would say that we've got pretty low confidence that underneath there is resistive. That's actually going back to the resistive model for the inversion. So in this case, those models really fan out. So we will be more inclined to say that's not the basin, that basin, and I would tend to do an interpretation just like that. Because that's about as much we can get from the data at this stage. So there's been a lot of consideration into this, and that's another thing that we consider right at the start when I was talking about the different things that we input into our interpretations, understanding that these are one model of potential hundreds of thousands. It has to be in the back of your mind that it's just going to be the best we can do with what we've got at that time. Yep. No, I actually have not done that. No, that's a good point though. Yeah, I actually don't even know where I would access ground EM data from. But BinView, all right. Haven't done any or much interpretation in New South Wales yet, so yeah, I'll keep an eye out for that. I'm not too sure how well, how helpful it will be at the scales we interpret as well, because when we're doing such regional work, we could get one little point basically, or like a small postage stamp. For the national scale, it might give us a very small amount of information for the scale that we're working at, but it is a very good point, and I'll take that on because it's actually yeah okay.
You mentioned attributing your line work early on. Are you using a universal standard set of attributes, or is it bespoke for each area?
So as part of the workflow, we have mandatory fields which have mandatory inputs. So, and that's it's all detailed. So they have to be like a universal standard, and then that's for, say, basis of interpretation or contact type or confidence levels or anything like that. For the stratigraphic unit information, that has to be consistent with the strat units database. And then we have free text fields as well for comments, new observations. So if you see a fault that hasn't been documented before, we can capture that with free text fields. We have interpretation reference fields, which are also free text. So a bit of both. We have the standardized inputs, and then we have free text fields as well.
And you mentioned the line work is available through ECAT.
Yeah.
Is that line work to be imported into 3D software or the GIS software?
Both. So we've developed a new it's a format that can go into GoCAD and maintain the attributes, because we couldn't do the interpretation in GoCAD because of the attributes that we need to capture. But going back the other way, Malcolm Nicol has been hard at work at developing a new format that can go into GoCAD, and then we can actually filter the data. So say you want basis Cenozoic of overlying the rolling downs group done by this interpreter, you can just put all those filters in and bang, it will spit it out. So we still maintain those attributes in our 3D data that we're delivering. We also deliver it as the points as well. So you can bring those just as with XYZs, you can just chuck them into anything. They can go into GIS packages, they can go into 3D packages. We maintain the segment and vertex ID, so you can take those points and stitch them back into the line segments in your given software as well. So. No, I can't see anything. Nothing online.
Just one more question. Located PNGs.
About them, yeah.
Well, I know it's very handy. I think in the download packages for AUS AEM, you have located PNGs that can be pulled straight into
GIS, yeah.
And would the same thing be available? Was that going to dumb it down too much?
That's a good question, because that's like you mean if we could generate the interpretation, turned 90 degrees located. We haven't done that. We haven't considered that. But it's that's a good consideration. One thing about those PNGs though are they sort of fit a line of best fit, so they squash up and then they're stretched in areas. So that would also do that to the interpretation if we had to do that. But that's we haven't considered that, but it's a good point.
And my last question: has Geoscience Australia had much discussion about the line spacing to use for these big surveys? It seems like 20 kilometres is sort of the standard you use, but a lot can happen geologically in 20 kilometres.
Yeah, I agree, and I think what we do is the infill in areas. So we'll use the 20 kilometres line spacing as a guide for what's in the general area, and then do infill in those areas that we can see, well, maybe we need more detail here. So there have been infill programs to get higher resolution in some of those areas. We have to also consider that we are working at a national scale, and there's always going to be a compromise and a trade-off between, well, we could do 5 kilometres, but we're not going to get as much of the country done. We could do 20 kilometres. Personally, as someone that's not as involved in the acquisition or anything, but in the interpretation space, for a national scale, I think that 20 kilometres is super handy, as you saw in some of those earlier slides where we were looking at things that tracked for like hundreds of kilometres. So we're looking at like those large scale, first order structures, and what the AUS AEM is good for is actually giving people that general national scale overview, to guide them into other areas. If they want to do a high resolution survey, then, you know, then they've got that baseline.
Do you have any questions? If there's no questions online, okay, then we close the talk. Then thank you, Seb.
No worries. Thank you. Thank you all for listening.